So eventually we're going to get to a more analytical way of actually finding the value of a definite integral. But before we do that, what we want to do is be able to use geometry to find the value of a definite integral, which we can do if the area under a particular curve is a shape whose area we already know how to calculate. So I've put up here one simple example of that. Let's evaluate the integral from -1 to 3 of the absolute value of x dx. So first thing you'd want to do, since we don't yet know how to evaluate this, is let's actually draw the graph of what we're trying to integrate. We can see is actually one more green. There we go. One, no, sorry, 3, 2, 1. There we go. Okay, so this function, absolute value of x, we know that it looks on the interval -1, 3 is going to look like this. It's going to go down there, hit a vertex at the origin, and then it's going to go up here like this. So the integral from -1 to 3 of that function is going to be the area bounded between the function and the x-axis. So we can do is we can draw these boundaries in here like this. We know that those are the left and right boundaries at -1 and 1. And what we're doing is we're finding this area that I'm shading in yellow. And there we go. Okay. For some reason the pen was not drawing it very nicely. Okay, so fortunately, what this is just two triangles whose base and altitude we know. What we can see is that on the right we have a triangle whose base is of length 3 and whose height is of length 3. So, so therefore we can see that this triangle has an area of 1/2 base height, 1/2 3 times 3, which is 9/2. And this triangle, we have here a base of 1 and a height of 1, so the area of this triangle is going to equal 1/2 times 1 times 1, which is just equal to 1/2. So the total area that we're looking at is equal to 1/2 plus 9/2, which is 10/2 or 5. So that's the area that's the area that we can see here. So therefore, we can conclude, keeping in mind an integral it's not synonymous with area. It's a way of calculating a certain type of area. We can see that the integral is -1. The integral from -1 to 3 of the absolute value of x dx is equal to 5. So there we go. Just using the fact that when we have a positive curve, when we have a positive function, the area under the graph of that function is equal to the integral of that function on the relevant interval. So this is the value of that integral. So here's another example of how we can use geometry to evaluate an integral. So here we have the integral from -2 to 2 of square root of 4 minus x squared dx. Now the thing to recognize, hopefully you do recognize this, is that square root of 4 minus x squared is actually on the interval -2 to 2 is actually just the upper part of a circle of radius 2. Now how do we know that? We know that because the equation of the circle of radius 2 is x squared plus y squared equals 4. So if I solve for y, I get y squared equals 4 minus x squared, or y equals plus or minus the square root of 4 minus x squared. So the positive is going to give us, positive square root is going to give us the positive y values, in other words, the upper part of this circle. There's also a lower part of the circle given by the negative values, but that's not the part that we're given in this integral. We're only given the top half of the circle. So what we're really doing is finding by the way, since the circle intersects the x-axis at positive and -2, we can see that the shape that we're being given by this curve is really just the area. It's this purple curve, and the integral is giving us the area under the purple curve, or specifically the area of this yellow region. In other words, the area of a semicircle. So what we simply have to do is find the area of a semicircle. Well, we see that this is a circle of radius. Oops, this is a circle of radius 2. That's radius is 2. So we know that the area of circle of radius 2 is equal to pi times 2 squared, or 4 pi. So it stands to reason that the area of a semicircle of radius 2 is equal to, let's that's just my way of writing radius 2, must be equal to 2 pi, or half that area. So we're not being asked to find the area of a semicircle, we're being asked to find the value of an integral. We just have made an argument that that has to be equal to the area of that semicircle, because that's the area under this curve. This is the curve y equals square root of 4 minus x squared. So that means we can conclude that the integral from -2 to 2 of the square root of 4 minus x squared dx is equal to 2 pi.